in analog design, typically we deal with two-pole systems max. Sometimes you end up with there might be multiple poles. There will be, not might be, there will be more than two poles in the system. But the poles, let's call this as omega p3 up to omega pn, will be at frequencies where magnitude of the gain, whatever gain, it can be a voltage gain, current gain, GM, trans resistance, whatever it is, magnitude of the voltage gain is less than 1 at these, will be at frequencies where AV is less than 1. Okay, so basically bottom line is we will have multiple poles, but we design the system in such a manner, we place the poles at such places such that these higher poles, higher order means omega p3 until omega pn, will be at frequencies at which the gain is less than 1, and we'll justify this. Why this will justify later. Why this will be justified later. Will be justified later. Okay. So hold on to this thought because this is important. So sometimes we have three poles also, but it becomes a challenging thing to design, and we have to do something special to make sure that it finally becomes a two-pole system or something like that. So we will get into that. Now, the next thing that I wanted to say is that Bode plot is an asymptotic plot. Bode plot is an asymptotic plot. Okay, so we'll explain what that plot means. So in order to understand that thing, so we will write a transfer function h of s in this manner. Is there a chat or something that I see? Some chat is there? No. Okay. 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 So h of s, Bode plot is an asymptotic plot. Now, in order to, we will write the transfer function as a midband, okay, and 1 plus s by omega z1, 1 plus s by omega z2, sorry, like this, 1 plus s by omega zn, and the poles as 1 plus s by omega p1, 1 plus s by omega p2, 1 plus s by omega pm. Okay, so m poles and n zeros. Okay, always m will be greater than equal to n. That is important in the system. Now here another thing is, another note is that omega p1, omega p2, omega pm are all positive numbers, or if real poles, or have positive real part. Okay, if they have positive, if omega p1 are all positive numbers, then the poles are in the left half plane. Otherwise, they become on the right half plane, which is physically not possible. Any physically realizable system should have the, sorry, I take it back. Any system that you, I would put it in this manner. If I realize any passive system using resistors, capacitors and all, that would actually be such that the poles will be on the negative half plane. But if I have an active circuit, then okay, let me not state that, because I am introducing open loop and closed loop, all these things come in. So let's not get into that at this point, because I have not introduced what is a loop yet. Okay, so omega p1, omega p2, all these are positive numbers, means the poles are in the left half plane if they are real poles or have positive real part. Okay, that means if it's an for complex number, then they will of course come in complex conjugate pairs. Okay, yeah, that means there will be omega p1 and omega p2 will be complex conjugate of omega p1, but the real part of both of them will be negative, so that the overall pole location is on the left half plane. But the zero location, omega z1 can have positive or negative real part. Real part. Okay, so this is important. So these are certain things about the transfer function. So from now on, we will consider the transfer function in this manner. Okay, am I clear? Okay, so now we will, yes.
Sir, in that statement that omega z1 can have positive or negative real part, we are talking about all the zeros, right?
All the zeros. Omega, sorry, not omega. What did I write? Sorry.
Sir, you wrote only omega z1.
Omega zi is zi. For I equal to, so I'll put an arrow here. For I equal to 1, 1 to n. Okay, for all zeros. Yes, thank you for correcting. Okay, so now now the next thing is we will draw the Bode plot. In order to draw Bode plot, we have to find out. Okay, so first we'll start off with a one pole system. Let's start with a simple one pole system. One pole system. So the one pole system, it doesn't have zero, so it will be given as A divided by 1 plus S by omega P1. So it has only one pole. This is how we are doing it. Okay, so now it is an asymptotic plot, means I will plot the magnitude response. The Bode plot has two responses. One is the magnitude response and the other is the phase response as a function of omega is the frequency axis. Okay, and this is the gain h of j omega magnitude. So keep in mind it is h of s, but I'm computing the magnitude along the j omega axis of the s plane. So s plane is like this. So this is the s plane. So sigma and j omega axis. So I am always, when I'm plotting the Bode plot, I'm applying a signal along this y-axis. That means I'm applying a sine or a cosine waveform which is traversing along this axis. Okay. So that's why we write it as the magnitude of h of j omega, and this magnitude is typically expressed in terms of 20 log to base 10 of this, which turns out to be in decibels. Okay, this is the common. So y-axis will be in decibels, and the x-axis can be either in degrees, sorry, not Celsius, sorry, degrees or in radians. Okay, it will be in degrees. So I'll write degrees rather than this dot. It will be in degrees or radians. Okay, so that is the phase. So for this class, we will do it in degrees. Okay, for this course, we'll do it in degrees because it gives better understanding. So the y-axis. So this is the magnitude plot. This is the magnitude plot. And this is the phase plot. So Bode plot has two parts. One is the magnitude plot and the second is the phase plot. But we said that it is an asymptotic plot. So when you are trying to draw an asymptotes, which I don't know if you have done it in your +2, you must have done some asymptotes and coordinate geometry, all those plots and all. You put in some extreme frequencies first. Okay, so put omega equal to j omega. So I'll make it j omega equal to 0. So what is the gain? Gain will be a, so 20 log of a. So this point is 20 log to base 10 of a. And then I put omega j omega equal to infinity and compute the magnitude. It goes to minus, goes negative, right? It goes below 0. It goes towards infinity. It approaches infinity. Correct? Now, what about the phase? When j omega equal to 0, what is the phase? Phase is 0 degrees. So this is 0 degree. And when I put omega equal to infinity, the tan inverse of infinity, right? Which is how much? Omega, sorry? How much? When does tan go to infinity? So what is the phase? So the magnitude. So let's plot the magnitude. H of j omega is what? Is equal to 20 log of a divided by square root of 1 plus omega squared omega p1 squared. Correct? And phase of h of j omega equal to tan inverse of minus of, what is it? Omega by omega p. Am I clear? Is that okay? Okay. So this is the phase. The negative sign comes because it is in the denominator. Okay. So now we have, so this therefore is can be written in terms of this magnitude, this thing. And note that this is log to base 10. Okay. So now this is there. So that means as omega approaches infinity, this is going to approach infinity, 90 degrees. So it never reaches in real frequency. When you're in the lab, you'll never hit 90 degrees phase shift. Okay. And otherwise it will be 0. Now asymptotic plot. So now what we will do is, let's try to find out what is the magnitude at omega at the pole frequency. That means when I apply a sine wave of frequency omega p1, and let's say omega p1 is a real number, okay, then of course can omega p1 be a complex number here if it's a single pole system? Hello? Can omega? Why not?
Sir, because then a conjugate will also be there, so it will become two pole.
It will become two pole. So that means there will only be, that means omega p1 is a real number. When you apply that real number, what is the magnitude here? What is the magnitude? The original magnitude here is 20 log of a.
20 log a minus 3.
So magnitude, this is at omega equal to 0. I don't know why is this erasing it. So it is going to be 20 log of a at omega equal to 0. It is going to be 20 log of a minus 3 dB at omega equal to omega p1. So that means at omega p1, I will get a magnitude which is 3 dB lower than this. This difference is going to be 3 dB. Now, my plot is therefore going to actually cross like this, and it will be going down. Okay. Now I have drawn a straight line here. Okay. Now, can you show that If I plot it in dB, this is going to be a straight line. And omega is in log scale. This will become a straight line. Can you prove that? If omega in log scale, this is omega in log scale or linear scale, here it doesn't matter, but we draw the magnitude plot in log scale. If we do that in log scale, then it will go down linearly from this plot. Can you prove that? When that means log of omega, okay, that as a function of log of omega, this will be a straight line. So now if I have a straight line like this, what should be the slope of the straight line? This should be equal to minus 20 dB per decade or minus 6 dB per octave. So what is the meaning of dB per decade? Means if I have a magnitude of 0 dB at, let's say, omega 1, and if I have a slope of minus 20 dB per decade, means at 10 times omega 1, which is 1 decade, the value of the gain is going to be minus 20 dB. 6 dB per octave means at twice omega 1, it is going to be down by 6 dB. Okay. So now this is a plot. So we knew what was the frequency at 0, what was the magnitude at 0 frequency, what is the magnitude at, we know the magnitude at omega at the pole frequency, but we are saying we are drawing an asymptotic pole. So what we do is we draw an asymptote to this curve. So this curve will actually go down like this. This is no more an asymptotic curve. It has a bend. So when we draw an asymptotic curve, what we do is we draw a straight line like this. And right at the pole frequency, we start drawing a straight line which goes at minus 20 dB per decade. This is an asymptotic plot for a one pole system or a Bode magnitude plot which goes like this at minus 20. At the pole frequency, but the gain is minus 3 dB. Keep that in mind. But then in an asymptotic plot, we draw a straight line like this, one asymptote and another asymptote. Wherever it intersects, that intersection point is called omega p1. Am I clear? Is that clear to everyone? What is an asymptotic plot? What needs to be done? Okay. So now about the at that same omega p1, what is the frequency? It is going to be minus 45 degree. So and now this will be an asymptotic curve which goes like this, and this omega p1 it will hit minus 45 degree. So this is the tan inverse function, okay, which starts like this and approaches minus 90 degree as omega tends to infinity. So for a single pole system, that means what we see is that when a pole comes in, I start rolling off at 20 dB per decade. Okay. So now let's look at a two-pole system. So if I have a two-pole system, so we will write it as h of s equal to a divided by 1 plus s by omega p1 times 1 plus s by omega p2. Okay. Now when we are drawing this plot, let us assume that omega p1 is the dominant pole. We have already defined what is dominant pole. Let us assume that omega p1 is a dominant pole. What is the meaning of omega p1 is a dominant pole? Means omega p1 is less than omega p2. The frequency of that is less than that. That is the dominant. We'll also assume, let us assume omega p2 is much greater than omega p1, implying omega P2 is at least 10 times omega P1. It can be more than that. So we are assuming this. This is an assumption for us when we are doing any diagram in the class. But if you are doing anything in the lab or with MATLAB or Python, then we don't need to have this assumption, because for the class we need to make sure that we are able to draw the asymptotes correctly. Okay. Any questions? Any questions on this? Okay. So now let's draw the magnitude plot first. So this is h of j omega. So I'll do it like this and write dB here. Means automatically 20 log we are taking. This is the normal convention. Okay. This can be done. So now we put in omega here. Let us mark omega P1 here and omega P2 here. So now when we are close to DC, my gain is 20 log of A. So we mark this point. When at infinity, my gain is going to be minus infinity. Okay. Now let's see what happens when my gain, when we are at omega P1. At omega P1, okay, omega P2 is much greater than this. So I substitute omega P1 here, omega P1, then this number will be much smaller than 1. So I can ignore the second term. So for this frequency, this system behaves like a single pole system, means at this frequency, if I draw the asymptote, the gain here drops to minus 3 dB. It starts rolling off at minus 20 dB per decade. Sorry, minus 20 dB per decade. It keeps on rolling, and at omega P2, at this point omega P2, if I plug in omega P2 here, okay, and omega P2 here, you will see that it further drops off from there by 3 dB. Whatever is the value we are getting by 20 dB per, it will drop down by 3 dB. But this term will be a very large number. Okay. So this term would no more define the slope at this point. This will define the slope. Now another slope will be added. It becomes another 20 dB per decade. Means at this point it will further start rolling off at, and so it will start rolling off at minus 40 dB per decade. Okay. So at omega, as soon as it hits a pole, it starts rolling off at minus 20 dB per decade. Second pole, it starts rolling down at further minus 20 dB per decade. So it becomes minus 40 dB per decade. Okay. Now let's look at the phase plot. Now the phase plot for two-pole system. So what will happen is, so it is like this. It goes to omega at 0. We know that at 0 frequency, so we have h of j omega equal to A divided by 1 plus j omega by omega P1, 1 plus j omega by omega P2. So I hope you know why we are writing j omega, because we are plotting along the j omega axis. We are sweeping the frequency. That's what you do in the lab. Your signal generator is sweeping along the j omega axis. That's all it is doing. So at omega equal to 0, these terms vanish. So the phase is 0 degree. Omega equal to omega P1. Okay. That time omega equal to omega P1. This term will be very, very small. Tan inverse of a small number, because omega P1 is much, much smaller than omega P2. Tan inverse of a smaller number is 0. So tan inverse of only this is dominating. Okay. So therefore we'll have minus 45 degree at omega P1. Okay. So we will have a minus 45 degree. Now at omega P2, at omega equal to omega P2, this number will be large, right? So it will almost, this part will give 90 degree phase shift, and this part will give you 45 degree phase shift. So the total phase shift at omega equal to omega P2 is going to be minus 45 minus 90, which is minus 135 degrees. And then it approaches minus 180 degree as omega keeps on approaching. So my question is, will the frequency of this two-pole system ever reach minus 180 degree? The answer is no. So the phase of two-pole system two-pole system never reaches minus 180 degrees. Phase of one-pole system never reaches minus 90 degrees. Okay, so this is what is going to be this thing, minus 180 and minus 90 degrees. Okay, now this is the overall the phase response of the single pole and two pole is going to look like. So the bottom line is, if I have to draw, if I have now a three pole system, what happens? Three pole system. So that means if I draw the gain 20 log of h j omega magnitude. So this is omega in this is log scale, by the way, log scale. Okay, so let's say the poles are at omega p1, omega p2 and omega p3, and let's draw the phase over here. So in the omega p1, omega p2 and omega p3, this is the angle of h of j omega. Now assumption, again we are assume omega p2 much greater than omega p1 and omega p3 much greater than omega p2. Okay, this is done for our class sake. For the class we are doing it so that it is easier to draw the plots. So here it will be A, the DC gain. Now you understand why it is called the DC gain, because we want to, this is why we did whatever we did in the DC gain. Then we found out the pole location. You hit a pole. Okay, so it will hit the pole first, start rolling off, and the slope here is going to be minus 20 dB per decade. Then it comes down, hits another pole and starts rolling off at, sorry, okay, I'll draw it in a better way. Okay, so it will start rolling off at 20 dB per decade. So this slope here is minus 20 dB per decade. Then here it starts, I'll make the slope a little larger. So here it is going to be minus 40 dB per decade. And after it hits the second pole, it will go down sharply at minus 60 dB per decade. Okay, and the phase at this pole is going to be minus 45 degree. From another one pole to the next pole, the phase changes by, they should make these tablets with matte finish so the friction is more and pen doesn't slide like this. So this will become minus 135 degrees, and at omega p3 it will be another 90 degree. From 135 it is going to be minus 225 degrees. So it is going to look like this, a tan inverse like this, going like this, and then approaching 270 degrees, 270 degrees at infinite frequency. It will never reach 270 degrees. Okay. Am I clear how the Bode plot needs to be drawn when there is a pole, different poles? So if there is a fourth pole, then it starts rolling off at minus 80 dB per decade. Any questions on this? Now, if this assumption is violated, okay, then it becomes a little tricky to draw this, but the asymptotic plot, there will be initially it will be minus 20, then it starts changing at minus 40 somewhere in between, and it becomes a little tricky to draw by hand, but MATLAB of course gives you the plot and tells you how much it is going to roll off. Okay, suppose I have 3 poles right here itself, then what should be the slope from here? It will go down at minus 60 dB per decade, right here itself. 3 poles at the same location. Okay. So now all these we have talked about are real poles. All these are for real poles. How would the Bode plot look? How would the Bode plot look? Bode plot look when there are complex conjugate poles. I'll give some homeworks in which you are going to do MATLAB exercise. Am I clear? So you need to do this in the homework. So you will see some peaking and all. So if there is a complex pole, you will see that this will go up and then starts coming down. And if an imaginary pole means it will reach infinity and it will come down like that. Okay, there will be resonance at that point. So that's called a resonance. So it will go like this and it will start coming down. Okay, so any questions on the poles and how to draw the Bode plot? So now here is the thing. From the Bode plot, you should be able to write down the transfer function. From here to the transfer function, you should be able to do. And from the transfer function to the Bode plot, you should be able to do vice versa. Am I clear? Any questions on this? If I give you a Bode plot and tell you, can you find out what is the transfer function of the system? Okay, you can do that because you will identify the poles, and once you have identified the poles, you get the transfer function. Write it in this format. Write it in this format. Any questions so far? There is a chat. I don't know why it is taking. So somebody put something in the chat. Where is it? How minus 20 dB per decade comes in? How minus 20 dB per decade comes in? Can anybody tell me how minus 20 dB per decade comes in? Let's prove this now.
So if we put delta omega and solve it, then I guess it should come.
Yes, the slope.
H of j omega magnitude equal to 20 log of a divided by square root of 1 plus omega squared by omega p1 square. Correct? So this is going to be 20 log of a minus 10 log of 1 plus omega squared plus omega p1 square. Correct? Now, omega p1, okay, at this point it is minus 3 dB, and after that, let us say I take a point over here, omega, and I want to find the slope at this point. So what will I do? I will, that at this point, any omega, this term will be greater than 1. Yes or no? The square of that. So it will be 20 log of A minus 20 log of omega by omega p1. So equal to 20 log of A minus 20 log of omega plus 20 log of omega p1. I am plotting this as a function of log of omega. This. So what is the slope of this? So y equal to mx plus c, where m equal to minus 20, x equal to log of omega, okay, and c equal to 20 log of A plus 20 log of omega p1. Does it answer your question? Yes or no? Subhadeep Nandi? Yeah, is this okay? Okay. So similarly, you can prove, yes.
सर वो 1 प्लस ओमेगा स्क्वायर अपॉन ओमेगा पी स्क्वायर को मतलब 1 को इग्नोर क्यों किया?
So अगर ये 2 है, right? और ओमेगा is twice of omega p1. Then ये कितना होगा? 4 होगा.
Yes sir.
And अगर ये 3 है तो ये 9 होगा. So it's an asymptotic plot I am drawing. So 4 is relatively the summation log of 4 versus log of 5. How much is the difference? Not much, right?
So sir हम ओमेगा को ओमेगा p1 से मतलब ग्रेटर देन लेके चलेंगे ज्यादा बहुत ज्यादा
लेके चलेंगे मतलब it is right. After I am plotting at this, below this it is this. I am all it omega this is minus 20 dB per decade when omega is greater than omega p1. That is what we have
just
drawn.
after नहीं होगा ना वो
Just after, that is why I am not drawing an exact plot. It is an asymptotic plot. Asymptotically, what will be the slope? That is why. So it is.
Okay,
this is an asymptote we are drawing, right? We are not a computer. We are drawing. We are human beings. We want to draw an asymptotic plot. Okay. So basically, it won't be either pass में exactly 20 dB नहीं होगा. It will be 20 dB at a much higher frequency, minus 20 dB per decade at a much higher frequency. Okay. So that is what will come out that you will get. Does it answer your question?
Yes sir.
Okay. Okay. So now let's.
The other unit, the octave one.
Sorry.
You mentioned another unit, an octave one.
Octave is twice the frequency.
Okay.
Octave is twice. So 20 dB per minus 20 dB per decade equal to minus 6 dB per octave. So either twice omega de do, then what will you get? You will get minus 6, right?
Okay.
So that is what will happen. So basically you plug in omega equal to omega p1 here, you get minus 20 log of 0, right? 20 log of 1, which is 0. At omega equal to 10, what will you get? Log of 10, which is 1 minus 20. So that is why it is 20 dB per decade. Okay. So here this is obtained by assuming omega squared by omega p1 square is much greater than 1. A good approximation in case of asymptotic plot. Okay. We are not drawing exact, keep in mind, we are human beings. We want to quickly analyze. Calculator computer nahi hai. The computer, you can give anything, it will do correctly. But we have to do rationally and draw conclusions from there and see whether the system works or not. That is why we are doing these things. Okay, finally we rely on the simulator. Okay, so now we have seen. Now let us
Sir.
see what happens. Yes.
Sir, if two poles coincide,
Yes.
then there is a roll off of minus 6 dB. But
Minus no, roll off of minus 20 dB, 40 dB per decade, minus 40 dB per decade.
40 dB per decade. I was saying about the roll off. I mean minus 6 dB.
At that point, yes, it will be minus 6 dB down from
Yes.
the DC value. Yes.
Yes, but we usually define the cutoff frequency as minus 3 dB. So how these two things matches with each other?
No, so okay. So if I have h of s equal to a divided by 1 plus s by omega p square, right? What is the 3 dB cutoff frequency? It is not omega p, because it will.
No, it is something.
Yeah, it will be something
Root
else. That time you define, you solve it and find it. So here it will be minus 6 dB down. If this is 0 dB, let me take this gain as 1.
So, sir, cutoff frequency is not always the pole frequency.
No, why should it be?
Okay.
Why cutoff frequency is the 3 dB bandwidth, half power bandwidth. Is that okay?
Okay, sir.
Okay. So now the effect of 0. So based on this analysis, what do you think will 0, how will be the asymptotic plot of a 0 look like based on whatever we have done? Can anybody give any hints? How would the, if I have, yes, h of s, let us say s, sorry, 1 plus s by omega z1. Is this system physically realizable? Is this system physically realizable?
No,
Why not?
because number of zeros is greater than poles.
Why? So?
The number of poles must be greater.
Why?
Sir,
You
it will
said.
not have a constant DC gain.
So? So why should the DC gain be constant? Why should the pole be there? Physically क्या होगा? देखो ये सिस्टम जो है at infinite frequency what is the gain?
Infinite.
Infinite. मैंने एक सिस्टम बनाया, कुछ एनर्जी दिया, कोई भी फ्रीक्वेंसी दिया, बट मैंने ये फ्रीक्वेंसी में इनफाइनाइट एनर्जी मिल रहा है, हाईएस्ट फ्रीक्वेंसी में, करेक्ट? इज इट फिजिकली पॉसिबल? You understand my point, right?
Yes, yes.
So that is not physically possible. Okay. So, or in other words, the area under the curve has to be bounded. Bounded input, bounded output, BIBO system. You have read about it, right? I am giving a bounded input, but I am getting an unbounded output here, right? Correct? So anyway, so this is physically not realizable. Physically not realizable. Physically not realizable. Okay, so this is there. So now let us try to draw the plot. So ye plot, how will it look like? At omega equal to 0, what is the value? 0 dB. At omega equal to 0. Omega equal to this thing, it is infinite, it is got omega log scale, omega in log scale, okay? It will approach infinity. Now, what will be the slope of this curve? It will be plus 20 dB per decade. Sorry, I made a mistake. At omega equal to omega z1, Until omega it will almost be this, and omega equal to omega z1 it will be 3 dB. But we have to draw an asymptotic plot, so I will draw 0 dB and a slope here which goes at 20 dB per decade. So the magnitude response due to the 0 will have a plus 20 dB per decade slope. Let's look at the phase response. Now here the phase response is tan inverse of omega by omega z1. Now we have said that if it is in the left half plane, that means omega z1 is positive, right? So if omega z1 is on the left half plane, that means omega z1 is positive. So I will get a phase of 0 degree at 0 frequency, phase of 90 degree at positive frequency. At omega equal to omega z1, I will get at infinite frequency 90 degree, I'll get a 45 degree phase shift. So I'll asymptotically approach 90 degree. This if left half plane 0. Is that correct? All of you with me? Zeros can be on the left or right half plane. That is not a problem. Now if I have a 0 on the right half plane, then it will go from minus 45 degree and minus 90 degree. Oh. So it will become minus 45 here. So it will start from here and approach minus 90 asymptotically. So the phase, the gain response at 0 will give a 20 dB per decade slope, and the gain, the phase is going to give me a slope of, will give me a positive phase change if it is in the left half plane, if right half plane 0. Any questions on this? Okay, so now let us take
Can you
a
please once more say what is left up plane and what is right up plane 0?
means the real part of omega z1 or omega z1. If omega z1 is a real, this is a real zero. Okay, this is a real 0, not a complex conjugate. Okay, complex 0 or an imaginary 0. This is a real 0. When I have a real 0, my 0 can be on the left side. This is the S plane, j omega axis. This is the sigma axis. This is S plane. My 0 can be on the left half plane or on the right half plane along the real axis. If it is on the left half plane, right, that means omega z1 is positive. If in this expression, if omega z1 is positive, then the 0 is in the left half plane. So left half plane 0 gives you a positive phase response, and a right half plane 0 gives you a negative phase response. Does it make sense?
Okay, sir.
Okay, everybody on the same page? So now, if I give you, let's say I give you a Bode plot like this. Can you please tell me what is the transfer function of this?
Sir, 1, 0 and 2 poles.
How many poles are there in this system?
So 3 poles.
3
Are you
poles.
Three
sure?
poles.
Sure.
So one pole at C, 2 pole at
Sir,
D.
4 poles.
Sir, four
Four.
poles. 4 poles, sir. 4 poles.
अभी 1, 2, 3 गिनते जाओ.
4 poles.
Finally decide where are the poles. Tell me.
4.
D1, C1, D2.
1 at B,
1 at
1
B,
at C,
1
2
at
at
C,
D.
2 at D.
So 4
Yes.
poles.
4 poles. And how many zeros?
1.
1, 0. So you can write down the transfer function now, h of s.
Yes, sir.
But can you write down exactly the transfer function? What more information do you need to write the exact transfer function?
सर एक फैक्टर से अलग हो रहा होगा तो
क्या फैक्टर कैसे कहाँ से
सर
फैक्टर
मतलब गेन हमें नहीं मालूम।
क्यों नहीं गेन पता है? ये तो दिया हूँ मैं 10.
अच्छा अच्छा सॉरी।
तो दिया गया है. मैंने ए का पॉजिटिव है या नेगेटिव है कुछ नहीं बताया, राइट? लेफ्ट ऑफ प्लेन में है या राइट ऑफ प्लेन में 0 है वो तो नहीं बताया. ये तो ऑब्वियस है. These will all be in the left of plane. Right? But this I have not mentioned. So that means you cannot exactly write the transfer function by just looking at the magnitude response. I have to give you the phase response to get the exact. But roughly you can say that it is going to be, there will be some factor A, 1 plus S by A, provided ये मेरी ओमेगा दे रहा हूँ. Okay. Then 1 plus S by B, 1 plus S by C, 1 plus
S by D square.
right? So either ये plus होगा या minus होगा, the phase response will only tell you. Am I clear? And what will be this value A? What will be this value A? 10 to the power of 0.5. Correct? Correct or not? Anybody has any questions on this? Is this correct or not? So 10 is the gain. So 20 log
sir.
of 10 equal to 20 log of A equal to 10. So therefore A equal to 10 to the power of 0.5. Okay, so this is your A and then you obtain all. Then you can mark this value. If I give you the exact number for this, you can tell me what is the gain at this point. So what happened here? This was giving 20 dB per decade, this 0 gave you 20 dB per decade. Then it hit a pole, plus 20 dB minus 20 dB becomes 0 dB. Then it hit another pole, 0 minus 20, it goes down at minus 20 dB per decade. It hit two poles, it goes down at minus 40 dB, minus 20 dB, it goes down at minus 60 dB per decade. Is this clear? And ऐसे ही filter design होता है. All the filters in the world that you are using, you decide on the Bode plot first, then you decide size of switches and resistors and capacitors to get exactly the poles that you want. So all the cell phone reception that you are seeing before there is something called an anti-alias filter. Alias filter, which is there in all the cell phones, computers, everything. In any analog system, it is there. And this filter is designed by first looking at the bandwidth response and doing all this analysis and then saying that, okay, I'll do it like this. Okay, any questions? Okay, so please.
So can you repeat the anti-aliasing filter?
No, anti-alias filter is nothing but a filter that is used in any analog system, because finally the system that you are using right now is a digital filter. digital system because it is a computer. So now, but the signals in the world are analog, right? Now the analog signal has to be digitized. That means you need to sample it. When you sample it, you have aliases. So I don't think you have studied this. Now, how do you overcome the alias? You put a filter before the sampling system. We call that filter an anti-alias filter. So the anti-alias filter, we know exactly what signals to pass and what signals to block. What signals to pass and what signals to block are defined by these values. And we plot those values on the x-axis and size the resistors capacitors accordingly. And that's how the filter is done. Okay. And then when you convert the signal back from digital to analog, again you need a filter which is called the reconstruction filter. Reconstruction filter. Again it is done in that manner. Okay. So it's an interesting area, and I don't think we have a course here. I was planning to. I think I'll start in another 2 years an advanced course on filter design and all in CMOS, how it is done. But it's okay. So it is not there at this point. Okay. Okay. So now with this, I think I would wrap up the frequency response. So the Bode plot will then we'll move on to current sources. Okay. So let's. Okay. So now what you are watching on the screen right now is nothing but you're watching your thing LED screen is nothing but the LEDs are controlled by a precise current source. Current source. Okay. And the amount of current source defines your intensity. So your intensity of LED. So there are red LEDs, R LEDs, green LEDs, and blue RGB LEDs. Okay, RGB LEDs are there. And if I have a display whose size is 1920 cross 1080, which is an HD display, you have close to 3 million LEDs, 2 million, 6 million LEDs. Each controlled precisely. And that defines the cost. That defines the cost. For your information, जो लोग सोनी टीवी खरीदते हैं, जो लोग एलजी टीवी खरीदते हैं, फिर जो लोग रिलायंस टीवी खरीदते हैं या मी टीवी खरीदते हैं, वो लोग सोचते हैं कि सोनी ने वो एलईडी पैनल बनाया है, रिलायंस ने वो एलईडी पैनल बनाया है, मी ने वो एलईडी पैनल बनाया है, but that is not the truth. Okay. There is an LED manufacturer, display manufacturer. Sony buys from that manufacturer, other companies buy from that manufacturer. But Sony finally qualifies that LED system, tests its quality and picks the best of them. Reliance will probably pick a lower end of them, and that is how the cost distribution comes in, the difference in cost. Sony does not manufacture that. Okay. So people are under the misconception that Sony does this, that is not the fact. Okay, there is, I think, a few LED manufacturers and LED display manufacturers, and the brands are defined by how they control the quality, and the cost therefore comes from there. They'll pick the best LEDs and all these things. Okay, so this is, now you see the importance of current sources, right? We need to generate these precisely controlled current sources so that I can have a very good display working at a very good speed. Because imagine 1920 by 1080 and I'm watching a cricket match or a football match in which players are running. I should be able to track each LED will turn on and off and change color and everything at that full speed. Imagine the sample rate at which it is 27 frames per second. Frames per second. Frames per second. And there are 6 million LEDs. And you have to do a scanning along the chain and display the image. So it is not an easy job. So this requires a something called a digital to analog converter, which does this, and that is typically a current steering DAC. So you guys are so used to this cell phones and all, you do not appreciate the amount of effort that goes into realizing these simple things. Besides, there is a touch screen and a lot of other things that are there. Okay, the LED screen has the touch aspect involved in there also. So anyway, so these current sources, so a lot of people do not appreciate why do we use this current source. What you are watching a beautiful current source in action at this point. Okay, which is changing this color to red and blue and all. Okay, so now let us see how do you realize a current source. So we already know that a BJT in saturation behaves like a current source. Behaves like a current source. Current source between collector and emitter. A MOS, in active region. Active region, sorry, somebody should have pointed. MOS in saturation behaves like a current source between source and drain. So now, building a current source, building a precise current source is beyond scope of this syllabus, beyond scope of this course. It is done using something called, it is done by using something called a band gap reference. So that will be taught in your 4th year. If there is an analog VLSI course, you can take that course, how to design precise band gap reference. We will discuss once we have a precision current source and current source. How do I realize millions of current source using that? Now I have your image. I want to generate millions of, if you are there, you have to generate millions of copies of that. What will you do? You stand in front of what? In between two parallel mirrors, right? So you mirror yourself infinite times and you have infinite copies of yourself, different scales and everything. This is where we realize something called a current mirror. Something called current mirrors to replicate precisely a precision current source. Precision current source. Realize something called current mirrors to replicate precisely a precision current source. Okay, so the called current mirrors. So now the next topic that we'll be discussing from next week is called current mirrors. Okay, so with this I'll stop today's class. Any questions for today's class, or any questions related to the test that you have? Is it clear to everybody? So those of you who are absent, okay, those of you who are absent, please communicate to those. So please communicate to those people who are absent. The fact what I told regarding the class test. Okay, I have not revealed the names of those who have resorted to something wrong. Okay, but there are 67 to 70 people with enough proof to suggest that they have resorted to malpractice, and they should be aware of this fact. Okay, so Alicia, do you